In July of 1994, scientists around the world watched in amazement as the comet Shoemaker-Levy 9 smashed into Jupiter. The impact's blast was so powerful that it unleashed a force equivalent to 300 million atom bombs. For 6 days, Jupiter was throttled by 21 separate impacts from the comet's fragments, which produced giant plumes of debris that rose 3,000 kilometers above the cloud tops, an impressive feat considering Jupiter's immense gravity, and heated Jupiter's atmosphere to temperatures reaching 30,000 degrees Celsius. At the moment of impact, the comet was traveling at a blistering speed of 216,000 kilometers per hour, with its largest fragment spanning 2 kilometers in diameter. The impact raised huge clouds of debris that were visible for months and left a scar in Jupiter's atmosphere more prominent than its great red spot. Now, collisions of this magnitude aren't entirely unheard of. Our solar system is littered with evidence of major impacts from comets and asteroids. Scientists believe Earth was hit by a massive asteroid at the end of the Cretaceous period, which likely led to the extinction of the non-avian dinosaurs. But these events are extremely rare, meaning the chance to see one in action is a once-in-a-lifetime opportunity. So, what did it look like? And does the incident shed light on the odds of a similar event happening here on Earth? I'm Alex McColgan and you're watching Astrum. Join me today as we relive the biggest planetary explosion ever witnessed from space and unpack what it taught us about Jupiter and planetary collisions. In 1993, astronomers Carolyn and Eugene Shoemaker and David Levy were conducting research at California's Palomar Observatory when they discovered a periodic comet that had been captured by Jupiter's gravitational pull. Periodic means that the comet has an orbital period of fewer than 200 years. This was unusual, as most comets in the solar system orbit the Sun. However, Jupiter is so massive, being the largest of the 8 planets by far, that its ability to capture other objects approaching its orbit isn't surprising. A lot of Jupiter's irregular moons are likely captured asteroids and comets that have since burned off their volatile material on their surfaces. But this comet also had other unusual characteristics. For one, it was big. So big that scientists think that the frequency of similar impacts is a 1 in 6,000 year occurrence. But the comet was also fragmented, most likely torn apart by Jupiter's tidal forces on a previous approach. Most striking of all, however, was its highly eccentric orbit. Eccentricity measures the deviation of an orbit from a circle, with 0 being the value of a perfect circle and 1 being the upper limit of when an elliptical orbit becomes hyperbolic. Shoemaker-Levy 9's orbit had an eccentricity of over 0.998, in other words, extremely eccentric. Almost immediately, astronomers realized there was a possibility the comet would collide with Jupiter, but their suspicion turned into certainty once they collected more precise data. Before long, astronomers knew the impact would occur sometime in July 1994, and pretty soon the whole world was waiting for the event with bated breath. Anticipating SL9's impact, astronomers monitored its movements from the Keck Observatory, Germany's Rosat X-ray telescope, and NASA's Hubble Space Telescope, among other instruments. But when the first of the comet's fragments hit on July 16, 1994, the worst-case scenario occurred. It looked like we would miss the spectacle. You see, SL9's trajectory meant the impact would occur on the side of Jupiter facing away from us. That meant none of Earth's high-powered telescopes were in position to view the initial impact. For scientists, this would have been a crushing disappointment. But as luck would have it, not all our cameras were located here on Earth. By sheer chance, NASA's Galileo spacecraft, launched in 1989, was only 1 year out from Jupiter at the time of SL9's final approach. It just so happened to be in a perfect position to record the impact as it happened. But Galileo wasn't our only helper from afar. The Ulysses spacecraft, which had been launched in 1990 to monitor the Sun, was also pointed at Jupiter. And even NASA's Voyager 2, located 44 astronomical units away, was programmed to monitor radio emissions from the crash site with its ultraviolet spectrometer. Each probe paused its own missions to work together on this to help us witness an extraordinary event. Shortly after Fragment A impacted Jupiter, Galileo saw a massive fireball erupt. reaching as high as 24,000 degrees Celsius. Its plume quickly rose 3,000 kilometers, which would make it as big as Australia from north to south. This was surprising, as scientists hadn't expected to see fireballs in the aftermath of the collision. A few minutes later, masses of ejected debris plummeted back towards Jupiter's surface and burned up, again turning Jupiter's atmosphere into a raging furnace. Before long, Jupiter's rotation brought the impact site into view of Earth, allowing high-powered telescopes like Hubble to view a huge dark spot on Jupiter. As it happens, Jupiter's rotation is fast, with days that last only 10 hours. Contrary to what you might think, larger planets tend to have shorter days than smaller ones. The comet's impact set off shock waves, which rippled across Jupiter's dense atmosphere at the speed of 450 meters per second. And all this was just from the first impact. For 6 days, between July 16th and July 22nd, the comet's fragments bombarded Jupiter, the largest coming on July 18th when fragment G hit. Its impact alone produced a blast 600 times more powerful than the world's entire nuclear arsenal, leaving a huge dark spot 1 Earth diameter across. However, as spectacular as the initial impact was, the comet's aftermath proved just as valuable. By studying the clouds of debris, scientists gained an unprecedented window into Jupiter's atmosphere and its movements. In addition, they caught a never-before-seen glimpse of Jupiter's composition beneath its dense cloud tops, as spectroscopic readings were able to identify material that had been splashed upward by the comet's impact. They detected diatomic sulfur and carbon disulfide, and heavy elements like silicon, iron, and magnesium. Interestingly, they also detected substantial amounts of water, something they weren't necessarily expecting. In fact, one of NASA's Juno probe's primary objectives is to locate where this water is hiding in Jupiter's atmosphere. However, one of the more disturbing implications of the impact was the realization that large celestial bodies could still hit planets. One school of thought theorized that major comet and asteroid collisions had been a lot more frequent earlier in the solar system's existence, but Shoemaker-Levy 9 made it clear that very destructive collisions were still possible. Had it happened by chance and we witnessed an extremely rare event, or does it happen more than we thought? Remember, we've only had the technology to see this kind of event within the last 80 or so years. If a comet as large as SL9 were to crash here on Earth, it would lead to the extinction of most life on the planet. This had a dramatic effect on our collective psyche. As anyone who lived through the 90s can attest, it was also a wake-up call for NASA and for various defense agencies. Before SL9, the term planetary defense didn't exist, but in its wake, NASA took up the mission of monitoring near-Earth objects, or NEOs, with the goal of identifying upwards of 90% of asteroids in our celestial neighborhood greater than 1 kilometer in diameter. Having achieved this goal, NASA is now well on its way toward identifying asteroids greater than 140 meters. But before you stay up all night worrying, be aware that these events are undoubtedly rare. And there is perhaps one other silver lining to SL9's impact. You see, Jupiter is a massive planet with a powerful gravitational influence. And since it is also one of the outer planets, some scientists now think it might act as a cosmic vacuum cleaner of sorts. We know that Jupiter gets approximately 2,000 to 8,000 times as many cometary impacts as Earth. So, perhaps one of the reasons extinction-level impacts are so uncommon here on Earth is that Jupiter had been a magnet for these kinds of comets and asteroids. This argument has even become part of the rare Earth hypothesis, which suggests that Earth is host to a unique set of conditions without which the evolution of complex life would be impossible. Not everyone agrees with this hypothesis though, and in any event, we're still a long way from proving it. So, while we might not know the exact likelihood of a massive comet or asteroid hitting the Earth, the impact of SL9 with Jupiter has certainly advanced our understanding of these events. Moreover, it was, without question, a spectacular moment that treated watchers to one of the most impressive action scenes ever witnessed by human eyes. Maybe one day we'll have the chance to see something bigger, but hopefully from not too close. While there have been other explosive events, like the 2022 Tonga volcanic eruption. For now, the winner is clear. The biggest explosion ever seen on a planet is Shoemaker-Levy 9, and by comparison, the competition looks like a drop in the bucket. Just past Jupiter, a comet has been randomly exploding for years, and no one knows why. These aren't cute little bursts. This is believed to be the most active comet in the solar system. We've seen it get nearly 300 times brighter in just a couple of hours, explode 4 times in 2 days without warning, and spew over 1 million tons of debris out faster than the speed of sound. And what makes it even stranger is there's no obvious trigger for the explosions. No dramatic swing into the sun, just a peculiar, icy body acting unlike anything we've ever studied. I'm McColgan and you're watching Astrum. Join me today on a tour of everything we know about Centaur 29P and why we think it acts out so violently, and the recent discoveries of the James Webb Telescope that flip these assumptions on their head. In 1927, 2 astronomers at Hamburg Observatory, Arnold Schwarzmann and Arno Arthur Wachmann, discovered Centaur 29P while comparing a series of photographs of the night sky. Initially classified as a short-period comet, 29P was later reclassified as a Centaur, the name given to a group of small solar system bodies orbiting the Sun between Jupiter and Neptune. They exhibit characteristics of both comets and asteroids, much like mythical centaurs were half human, half horse. It's thought that centaurs originated in the Kuiper Belt, but eventually moved inward due to the subtle gravitational influences of the gas giants over the last few million years. Centaurs generally have elliptical and unstable orbits. Most will eventually be flung into the inner solar system as comets join the Jupiter family comets, or be catapulted out of the solar system entirely. Because of this, centaurs represent a short-lived transitional state in a small body's journey from the Kuiper Belt to the Jupiter family comets. We think Centaur 29P could be launched into the inner solar system as early as 2038, when a conjunction with Jupiter will change the path of its orbit. But Centaur 29P is different from most centaurs in 2 big ways that will be relevant later. Firstly, its orbit isn't elliptical. It traces an almost perfect circle around the Sun. And secondly, it is big. Measuring 60 kilometers in diameter, it is wider than 96% of all centaurs and is one of the largest known cometary bodies. Oh, and it explodes a lot. It's the second most active body in the solar system after Io, exploding on average about 30 times per year, and 40% of these strong outbursts don't happen in any kind of predictable fashion. These explosions are erratic, sudden, and very intense. Following an outburst, the comet reaches peak brightness in about 2 to 3 hours. In 2024, it made headlines when it erupted 4 times in a 48-hour period, appearing almost 300 times brighter than normal. 2 years earlier, it shot more than 1 million tons of debris into space faster than the speed of sound, like popping the cork out of the world's most pressurized champagne bottle. The main outburst then triggered 2 smaller ones 5 and 7 days later, which seems to be a common occurrence for the comet. And even though those sound incredibly violent and powerful, things get even bigger. In September 2021, Centaur 29P underwent the largest outburst in 40 years when it blew its top 5 times in a row. Despite the massive blast, it wasn't scientists who initially noticed, it was amateur astronomers. This is one of the curiosities of Centaur 29P's history. Most of its eruptions are first observed by hobbyist stargazers. It's easier to pull out your backyard telescope and get approval to point a multi-million-dollar public-funded instrument on your special interest randomly exploding Centaur. When scientists heard what had happened, they managed to secure precious Hubble time to take a closer look, but the universe had other plans. As bad luck would have it, the day before the scheduled observation of Centaur 29P, Hubble experienced a technical glitch and couldn't be used. So what causes these outbursts? How do we know about Centaur 29P's properties that could possibly explain them? If you suspect volcanoes, you're kind of right, but not the hot, fiery kind. They are ice volcanoes. Centaur 29P is what we call a cryovolcanic comet. These are generally covered in an icy shell with ice, dust, and gas inside, mainly carbon dioxide, carbon monoxide, and nitrogen gases in a frozen, icy state. Over time, radiation causes the crust to weaken from solid to gas. This forces internal pressure to rise. Eventually, it gets too much and the outer shell cracks, unleashing a visceral eruption of cryomagma from the inside of the comet, a mix of frozen water, ammonia, salts, and volatile gases like methane and nitrogen gas. See? Ice volcano. Centaur 29P's nucleus has a high escape velocity, and most debris isn't ejected fast enough to break free from its gravity. The result is most falls back onto the Centaur's surface to reform its crust. This may then trigger the knock-on outbursts 5 or so days later, as we saw in the 2021 outburst. Around the comet nucleus, the ejected dust and ice particles form a hazy, reflective cloud, lingering for days, up to a couple of weeks, making the comet look brighter, sometimes by several orders of magnitude. Some cryovolcanic comets like 12P, also known as the Devil Comet for the horn-like plumes that form during its outbursts, are on highly elliptical orbits around the Sun. As you might expect, the closer to the Sun they get, the more active and volatile their behavior becomes. But Centaur 29P is on a circular, not an elliptical orbit. It's always roughly the same distance from the Sun, so you'd expect a pretty even absorption of solar radiation and regular, predictable activity. However, as we've seen, that's not the case at all. So why are these eruptions so erratic when they shouldn't be? What's going on here? Scientists have been trying to work out if there is any method to the madness of the Centaur's eruptions for years. Some have speculated that the eruptions may be related to its slow rotation period of 57 days. More specifically, they observed that major outbursts were more likely to happen every 52 to 60 days, but smaller outburst events also occurred every 30 and every 90 days, with enough regularity to make scientists think that there might be some kind of seasonal cycle governing the comet. While Centaur 29P's eruptions seem to happen quasi-periodically, they are utterly unpredictable in terms of intensity or precise timing. That didn't stop astronomers from trying to anticipate when our feisty friend would blow. In April 2023, scientists noticed the light surrounding the comet's nucleus had become fainter than ever, suggesting a slowed rate of outgassing. They predicted pressure was building up inside the nucleus at a faster and faster rate, making an eruption highly likely. And just like that, Centaur 29P gave off a mini outburst later that very same day. It was the first successful prediction of an eruption on this weird and volatile little world. For the first time, we weren't just reacting to randomness, we got on the inside track. It felt like a breakthrough, and thanks to James Webb, we were about to have another. Until recently, we had never detected carbon dioxide on Centaur 29P. Carbon monoxide was always seen as the driver of these eruptions, mainly because it is consistently found in high amounts around the comet. But in 2024, data from the James Webb Space Telescope showed us that that was only half the answer. Data from the previous radio wavelength observations of Centaur 29P showed a carbon monoxide gas jet pointed towards Earth, but Webb's near-infrared spectrograph brought the jet's composition into greater focus, revealing not just one, but two jets of carbon monoxide, one pointing to Earth and one pointing towards the north. And that wasn't all. The James Webb Space Telescope also revealed two jets of carbon dioxide emanating from the north and south directions, the first definitive detection of the gas on the comet. The difference in abundance of carbon monoxide and dioxide suggests Centaur 29P might not be one object, but several objects that have become stuck together. The cause of the outgassing itself? Well, scientists still can't say for sure. But one interesting theory has been put forth to explain the unusually high carbon monoxide levels associated with Centaur 29P. Carbon monoxide is extremely volatile, and pure carbon monoxide ice can sublimate at temperatures as low as 25 Kelvin. If it were stored near the Centaur's surface, it would have all escaped a long time ago, so it must instead be trapped or preserved deep below the surface somehow. One possible solution is amorphous water ice. Almost all the ice we know of on Earth is in crystalline form. Crystalline ice is characterized by a structured, ordered arrangement of molecules. Amorphous ice, on the other hand, is not tightly packed. This makes it less dense than crystalline ice, and it also means it can hold gases within its structure. At temperatures above 77 Kelvin, amorphous ice turns spontaneously into crystalline ice. The higher the temperature, the faster this conversion occurs. In this process, trapped gases are released. So in theory, if Centaur 29P still has amorphous ice in its core along with trapped carbon monoxide, and that ice is undergoing conversion into crystalline form, then that could be where the high levels of carbon monoxide are coming from. How plausible is this theory? Let's break it down. Centaur 29P started in the Kuiper Belt, with temperatures ranging from 30 to 40 Kelvin. At this temperature, all ice would be amorphous, since it only starts crystallizing above 77 Kelvin. As it traveled inward over 10 million years to its current location at 6 astronomical units from the Sun, temperatures rose to 115 Kelvin, and its amorphous ice started converting to crystalline ice. But how long will it take for all of its amorphous ice to turn crystalline? I mentioned earlier that Centaur 29P's size was going to play a role, remember? This is that part. First, researchers took 4 known small centaurs. They all measured between 1 and 6 kilometers across and were in a similar orbital position to Centaur 29P. They calculated that it would take those centaurs between 0.1 to 6 million years to convert their amorphous ice into crystalline ice. In other words, by the time they arrive in this position, they are already fully crystalline inside. All trapped gases released, no aces up their sleeves, predictable behavior. However, a centaur the size of 29P would take between 60 and 100 million years to convert all its amorphous ice. If these calculations are correct, it is possible the Centaur has only converted 50 to 65% of its amorphous ice, and this has huge implications for its behavior. Converting lower density amorphous ice into higher density crystalline ice would shrink the overall volume of the nucleus. This could induce structural failures in the Centaur's surface and interior. Some believe the subsequent cave-ins, landslides, and sinkhole creation events could be the driving forces behind the Centaur's erratic outbursts. But regardless of the elegant explanation, another problem exists. Centaur 29P doesn't slowly leak gas. It erupts explosively, sometimes multiple times per year. How that pressure is able to build up fast enough to elicit several explosions back to back in quick succession is still not fully understood. Why Centaur 29P undergoes such bursts of brightness and how its outgassing actually works remain two of the biggest areas of investigation relating to this highly active cosmic body. It challenges our assumptions of just how fiery icy bodies can be in the outer solar system, and we still don't know as much about it as we'd like. But we've made progress. We're slowly starting to unravel its mysteries, and thanks to incredible tools like the James Webb Space Telescope, we're only going to keep learning. What if I told you that there is a colossal structure that begins at the edge of our solar system? One that encircles our sun and all of the planets, but we've never seen it. A shell made up of billions or even trillions of ancient icy chunks the size of mountains marks the outermost boundary of our solar system, or so we think. Jaw-droppingly far away, beyond the reach of even our most powerful telescopes, the Oort Cloud is a region shrouded in mystery and speculation where the sun's influence grows faint as it brushes up against the void of interstellar space. What exactly is this Oort Cloud? If we've never directly observed it, how do we know it's out there? And why do some people question its existence? Let's find out. I'm Alex McColgan and you're watching Astrum. Join me today as we venture to the farthest reaches of our solar system and beyond to construct an image of this unseen astronomical wonder. You've probably heard of the asteroid belt and maybe even the Kuiper Belt. At two different locations in our solar system, these roughly donut-shaped bands of debris each move in the same direction, and more or less on the same orbital plane as the planets around our sun. The asteroid belt is the closest to the sun of these two debris rings, located between Mars and Jupiter, and consists of millions of orbiting asteroids. The Kuiper Belt, on the other hand, was first proposed by astronomer Gerard Kuiper as the origin of short-period comets in the mid-20th century. It is a massive field of icy debris out past Neptune. Occasionally, a piece of Kuiper Belt debris will get pushed by gravity, sending it on a new orbit closer to the Sun. In some cases, this creates a new short-period comet. These comets have orbits of less than 200 years and are often predictable as they continue to make subsequent orbits around the Sun. At the same time that Kuiper was investigating short-period comets, a Dutch astronomer named Jan Oort was contemplating the origin of long-period comets. Few scientists of the 20th century made more contributions to astronomy than Oort. In 1927, he calculated our place in the Milky Way galaxy, and in 1932, he was the first to find evidence of dark matter, to name a few examples of his discoveries. In 1950, Oort was the first to theorize the existence of a thick bubble of swarming, icy debris that surrounded our entire solar system, now known as the Oort Cloud. But unlike the asteroid belt and Kuiper Belt, it's still yet to be directly observed. To understand this theory, let me explain what led Oort to this proposition. Unlike comets with short orbits, such as Halley's Comet with an average period of 75.3 years, or Comet Encke with a period of just 3.3 years, long-period comets were unpredictable. For one thing, their orbital periods were so long that in some cases they could take as many as 30 million years to complete one orbit. And curiously, these comets came from all different directions and had various orbital inclinations. It was a mystery on the grandest of scales, but Oort noticed a few things that all of these long-period comets had in common. Their orbits indicated that these comets weren't coming from far out in interstellar space, but that their origin had to be closer to home. However, as I'll explain in a moment, not too close to home. So, if these long-period comets weren't coming from the Kuiper Belt and weren't coming from far out in interstellar space, where were they coming from? Oort found a peculiar similarity among the orbits of these comets, one that might provide the answer to that question. The point in a comet's orbit where it is most distant from the Sun is called the aphelion. Oort noticed that all observed long-period comets seem to have an aphelion that all grouped around a certain distance, around 7.5 trillion kilometers from the Sun. That's right, trillion with a T. As you can see, when it comes to the distances I'll be talking about in this video, our typical units of measurement fall a bit short. So instead of using kilometers, I will switch to astronomical units. 1 astronomical unit, or AU, is defined as the distance between Earth and the Sun, or about 150 million kilometers. So Earth is 1 AU from the Sun. The aphelia grouping that Oort noticed, where the long-period comets reached their farthest orbital distance from the Sun, was about 50,000 astronomical units. To help picture the orbits of these long-period comets, keep in mind that the outermost planet in our solar system, Neptune, is around 30 AU from the Sun, or about 4.5 billion kilometers. The main region of the Kuiper Belt extends from Neptune's orbit at 30 AU out to around 50 AU, but recent evidence from NASA's New Horizons spacecraft suggests a second region of the Kuiper Belt called the scattered disk, which continues to around 1000 AU. It's with these key findings from observed comets that they didn't come from far out in interstellar space, the orbital distances clustered around 50,000 AU, and the fact that they arrived from any direction and orbital inclination, that Oort theorized a special spherical swarm of icy debris that he believed to be the origin of long-period comets. In the years since then, mathematical models have shown agreement with the Oort Cloud theory, and astronomers have further theorized various mechanics by which the Oort Cloud came to be in its current state. The leading idea is that the Oort Cloud formed from ancient debris, leftovers from when our planet formed 4.6 billion years ago. After the planets formed, the surrounding area was still rich with these smaller, leftover chunks of material called planetesimals. The gravity from these early planets then scattered the leftover material in every direction. Some material was flung out of the solar system entirely, but a significant portion was sent into seemingly random, eccentric orbits around the Sun. These scattered planetesimals had eccentric enough orbits that they were influenced by gravitational forces outside of our solar system, while still remaining captured in our Sun's orbit. And it's believed that this is how these billions or trillions of icy chunks came to be part of the Oort Cloud. Gravitational perturbations can force Kuiper Belt objects out of place, creating short-period comets. We think that similar forces are what send Oort Cloud objects into elliptical orbits with the Sun, thereby creating long-period comets. These perturbations could be caused by passing stars or molecular clouds or tidal forces from the Milky Way itself. In fact, about 70,000 years ago, Schultz's star gained the title of the star that came closest to our solar system, actually grazing the outer region of the Oort Cloud. But luckily for us, it didn't cause any catastrophic disruptions to the Oort Cloud or our solar system at large. Schultz's star is a low-mass binary system made up of a red dwarf and a brown dwarf companion. So 10 millennia ago, even at a much closer distance to the Oort Cloud, the gravitational influence of this binary star was significantly weaker than that of our much more massive Sun. However, while most objects experience little to no impact during the low-mass star's brief encounter with the edge of the Oort Cloud, numerical simulations from 2018 concluded that Schultz's star is believed to have nudged at least some objects out of place, creating and influencing the trajectory of some long-period comets. But the Sun has been around for over 4 billion years, and that's a lot of time for other close encounters with stars in the distant past. Could these interactions have prevented the Oort Cloud from forming? Our models suggest no. However, Oort Cloud material may get exchanged with passing stars over eons. You see, other, more recent numerical simulations have suggested that Oort clouds could exist around other stars too. Our Oort cloud may also have both an inner and an outer region, each with its own distinct shape. Some scientists suggest that the inner region may be more like a disk, similar to the donut shape of the Kuiper Belt, while the outer region is suggested to form the spherical shell more widely associated with the Oort cloud. Altogether, the inner edge of this two-region Oort cloud may be 2,000 astronomical units from the Sun at its closest, with the far edge stretching all the way out into interstellar space, potentially reaching as far as 100,000 astronomical units from the center of our solar system. This means the Oort cloud could extend more than 1.5 light years across. To put that into perspective, since we're talking about very, very large distances, consider Voyager 2 spacecraft for a moment. As of the publication of this video, Voyager 2 has traveled to a distance of about 139 astronomical units from the Sun since its launch from Earth at 1 AU in August of 1977. That's about 3.3 AU per year, or about 56,000 kilometers per hour. It's the second farthest human-made object in space, just after Voyager 1. In August 2007, Voyager 2 passed beyond the boundary of the heliosphere, the outermost layer of the Sun's atmosphere. It extends out beyond the planets, and 3 times further than the distance to Pluto. Outside of the heliosphere, the Sun's constant flow of charged particles, called the solar wind, is finally impeded by the interstellar medium. And in November 2018, Voyager 2 finally crossed the final layer of solar turbulence called the heliosheath and continued on into interstellar space. Despite passing beyond the heliosphere and well past the main Kuiper Belt, Voyager 2 would still need to travel for another 300 or so years just to reach the innermost edge of the Oort cloud. That's how far away it is. And to fly through the Oort cloud, that could take another 30,000 years. Even when traveling at 56,000 kilometers per hour, it still takes all that time just to travel around 1.5 light years. If you've ever wondered why interstellar or intergalactic space travel is difficult, keep in mind that our nearest stellar neighbor is Proxima Centauri at around 4.25 light years away. However, some still question the existence of the Oort cloud, mainly because we're unable to directly observe it. Another argument has been made that long-period comets may come from other places, such as interstellar space. And in fact, the first observation of an interstellar comet, one that had origins from outside our Sun's influence, was made in 2019 by amateur astronomer Gennady Borisov. Professional astronomers joined in to collect data on Comet Borisov, named after its first observer. They found an unusual composition, a higher concentration of carbon monoxide than the average comet originating from our own solar system, suggesting that this comet may have formed in the presence of a red dwarf, a different type of star than our Sun. And yet, the vast majority of astronomers agree that the Oort cloud is really out there, despite the fact that we've never laid eyes on it. Plenty of indirect observations and mathematical models show great support for the theory, and the evidence continues to add up. But why is it exactly that we've never been able to see the Oort cloud? After all, with telescopes we can see stars far beyond our own solar system, and even the shapes of distant galaxies. The difference is size and light. Think about it. A piece of Oort cloud debris is roughly the size of one mountain on Earth. Let's consider Mount Everest at around 9 kilometers tall. Now consider the Oort Cloud's innermost boundary begins somewhere around 3000 AU, or roughly 450 million kilometers from the Sun. The distance from the Sun to the nearest piece of Oort Cloud debris is 50 million times the size of the debris. Talk about looking for a needle in a haystack. But more crucially even, is that stars and galaxies give off light, but Oort debris does not. The planets are relatively close to the Sun, so they are able to reflect the Sun's light and therefore are visible. Likewise, the asteroid belt and even the Kuiper Belt are close enough to the Sun that we can use telescopes to directly observe their debris. But outside of the heliosphere, the Oort Cloud is just too far and too dark for our telescopes to catch a glimpse. Despite the Oort Cloud's gargantuan footprint and pivotal role in shaping our understanding of the origin of many long-period comets, for now, we can still only infer its existence through mathematical models and indirect observation. But don't let our inability to make direct observations discourage you from following the evidence. I can think of a few other times in history when scientists put forth monumental theories despite a lack of direct observation. For example, in the 16th and 17th centuries respectively, Copernicus and Galileo put forth the theory that the planets orbited around the Sun, contradicting a widely held belief at the time that the Earth was the center of the solar universe. Their theory of a heliocentric solar system was not based on direct observation, but rather on indirect observation of the orbit of the planets. As we know, that theory turned out to be spot on. That's the thing I love about science and the pursuit of knowledge. There's always more to learn. The farther we travel through time, the better our understanding of the solar system will get. Who knows? Maybe in 100 years, future astronomers will have found a way to prove the existence of the Oort Cloud once and for all. Or maybe they'll have found a whole new explanation for long-period comets. Until then, the Oort Cloud remains one of astronomy's most compelling enigmas. In the dark, frigid void beyond Neptune lies a vast and mysterious region, where the ancient remnants of our solar system's birth drift silently through the darkness, perfectly preserved by the deep freeze of space. To reach this shadowy expanse from Earth, we must travel past the rocky planets, flying by Mars and then beyond the swirling storms of Jupiter and Saturn. Farther still, out beyond the blue giants, Uranus and Neptune, we finally reach our destination. Welcome to the Kuiper Belt, a vast ring of icy debris encircling our solar system like a frozen halo. This isn't just a collection of distant rocks, it's a time capsule from 4.6 billion years ago, holding the untouched building blocks of our cosmic neighborhood. It is home to several dwarf planets and mysterious objects that have left many astronomers scratching their heads. I'm McColgan and you're watching Astrum. Join me today as we explore the worlds lurking in the shadows of our solar system and piece together clues about its history, about planetary formation, comet activity, and even the origins of life. Before we knew for sure that the Kuiper Belt was real, astronomers suspected that something existed beyond Neptune. For decades, everyone's favorite dwarf planet, Pluto, was thought to be an isolated object in the outer solar system, but something didn't add up. Its small size and unusual orbit suggested that Pluto wasn't alone, and that maybe it was merely one of a number of yet-to-be-discovered distant objects. In 1951, astronomer Gerhard Kuiper predicted the existence of a belt of icy objects just beyond the orbit of Neptune, but without telescopes powerful enough to detect these objects, the idea remained theoretical for decades. That changed in 1992, when astronomers David Jewitt and Jane Liu discovered the first confirmed Kuiper Belt object, known as 1992 QB1. Pluto and its moon Charon, were both discovered before 1992 QB1, Pluto in 1930 and Charon in 1978, but these objects were only confirmed as KBOs after the 1992 KBO. Since then, thousands more Kuiper Belt objects have been identified, populating this distant region beyond Neptune. To grasp the true scale and position of the Kuiper Belt, let's imagine we're traveling in a spaceship, starting from the Sun and moving out towards the outer edge of our solar system. As we move along our journey, let's compare the Kuiper Belt to both the more well-known asteroid belt and the less well-known Oort Cloud. Starting near the Sun, we zip past the rocky planets, Mercury, Venus, Earth, and Mars. Between Mars and Jupiter, we see the asteroid belt, made up of the leftover materials from when our planets formed. A thin, spread out ring of rocky debris, the asteroid belt is about 2.2 to 3.2 astronomical units away from the Sun and about 1 astronomical unit wide. As a reminder, 1 astronomical unit is equivalent to the distance from the Sun to the Earth. Most of the known asteroids reside in this part of our solar system, ranging in size from the largest asteroid, Vesta, at 525 kilometers wide, almost the distance from London to Belfast, to the smallest objects, some of which are just tens of kilometers across. However, despite residing in such a large space, the total mass of all of the asteroids in the whole asteroid belt combined is only about 3% of the mass of the Moon. Beyond the asteroid belt, we encounter the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, colossal worlds that dominate the outer solar system. Finally, as we pass Neptune's orbit at 30 astronomical units, we reach our destination, an even more remote, icy frontier, the Kuiper Belt. This vast expanse stretches from 30 to 50 astronomical units and is home to a range of intriguing objects, from frozen relics of the early solar system to dwarf planets including Pluto, Haumea, Eris, Makemake, and countless other smaller objects. Like the asteroid belt, the Kuiper Belt contains ancient debris from our early solar system. In fact, Kuiper Belt objects are considered some of the oldest surviving pieces of our solar nebula that originally formed the planets of our solar system. And so, at one point in the very distant past, these stray pieces might have been able to come together to form yet another planetary body. However, Neptune's gravity prevented the icy objects from coalescing and never allowed them to form something new. Unlike the asteroid belt, which is primarily made of rocky material, the Kuiper Belt consists of mostly frozen methane, ammonia, and water ice, forming a frozen, thick, donut-shaped ring of debris. The Kuiper Belt contains hundreds of thousands of large icy bodies bigger than 100 kilometers across, and more than 1 trillion comets, not to mention smaller debris and dust. And the average distance between objects is so large it can be hard to imagine. Each of those objects is, on average, between 0.02 to 0.1 astronomical unit apart. Imagine 10 million kilometers between objects. Here, in the dim outer reaches of our solar system, these icy bodies drift in near silence, preserving vital clues about the origins of planets and comets. But it doesn't end there. That was just the main region of the Kuiper Belt. Overlapping the outer edge of the main region is another area of Kuiper Belt called the scattered disk, which continues out to nearly 1,000 astronomical units, with some Kuiper Belt objects on orbits that reach even farther beyond that. So while the asteroid belt and Kuiper Belt share some similarities, as you can see, one is vastly more expansive than the other. And while we may have reached the end of the Kuiper Belt, there's still another massive structure that surrounds every other object and belt I've mentioned so far. In a recent video, I talked about the Oort Cloud, the colossal structure of orbiting icy debris that encircles our entire solar system. It's so jaw-droppingly far away that even our most powerful telescopes can't catch a glimpse. So how do those two structures, the Oort Cloud and the Kuiper Belt, differ from each other? For one, the Kuiper Belt is thousands of times closer to the Sun than the center of the Oort Cloud, which is theorized to stretch from 2,000 to 100,000 astronomical units. Another major difference is that the Kuiper Belt is donut-shaped, while the Oort Cloud is spherical, like a gigantic bubble of swarming debris. But something these structures do have in common is that they are both sources of the celestial phenomenon that we know as comets. The Oort Cloud is the source of many long-period comets, while the Kuiper Belt is where some short-period comets are born. While the Kuiper Belt today is one of the most massive structures in the solar system, it's just a small fraction of what it once was. Originally, altogether, it probably contained 7 to 10 times the mass of Earth, but the shifting orbits of the 4 giant gas and ice planets cause most of that to be lost to space. What remains is no more than about 10% of Earth's mass. Not only that, but the Kuiper Belt today continues to slowly erode away. As objects occasionally collide and break apart, smaller fragments are left in their wake, and some of the resulting dust is blown out of the solar system by the solar wind. Sometimes these collisions, or Neptune's gravity, will cause Kuiper Belt objects to head on a new path towards the Sun, creating short-period comets which have orbits of less than 200 years. Over time, the Sun's radiation causes comets to shed material, producing the spectacular tails we see from Earth. Several famous comets originate from the Kuiper Belt or its scattered disk, including Halley's Comet with an average orbital period of 76 Earth years, or Comet Shoemaker-Levy 9, which broke apart and smashed into Jupiter in 1994 in the first ever observed collision of 2 solar system bodies. As we all know, Jupiter survived, but the impact was visible from Earth and was quite a spectacular sight to behold. You can see it out for yourself if you check out my video on the aftermath of this collision. You may also have heard in the news recently about a near-Earth asteroid named 2024 YR4. While there is a very small chance of this asteroid colliding with our moon, or even a smaller chance of it impacting Earth, the short-period comets originating from the Kuiper Belt pose no immediate threat to us in the next 100 or more years. In other words, you don't need to worry about that. Despite the Kuiper Belt being just a small remnant of what it once was, it still offers a nearly endless frontier of objects for us to explore. And unlike the Oort Cloud, which we have not been able to visit yet, we have been to the Kuiper Belt. While most of what we know about the Kuiper Belt comes from ground-based telescopes and the Hubble Space Telescope, NASA's New Horizons is the only spacecraft to have actually been there. It performed a flyby of the dwarf planet Pluto and Kuiper Belt object 2014 MU69, which was later officially named Arakoth, meaning sky, in the Native American Powhatan or Algonquian language. This flyby of Arakoth in 2019 was the most distant flyby in the history of space exploration, taking place 1.5 billion kilometers beyond Pluto, with the New Horizons spacecraft getting as close as about 3,500 kilometers above the surface of the object. And even among the swarm of mysterious objects that make up the Kuiper Belt, Arakoth still managed to surprise the New Horizons team. Its strange shape was unlike anything we had ever seen in our solar system. Arakoth is a small icy KBO known as a contact binary, composed of 2 distinct lobes that at some point merged into one body. Its shape resembles a flattened snowman. At just 35 kilometers long, 20 kilometers wide, and 10 kilometers thick, you might not think there's much to learn from this relatively tiny object, but what Arakoth lacked in atmosphere and diverse geology, it made up for in its unique structure. The bizarre pancake snowman shape of this Kuiper Belt object provides crucial insights into how planetary building blocks came together in the early solar system, and how planets may have formed. Arakoth's shape seemed to give it a counterintuitive gravity field and rotation, and several papers published since the flyby have led to an almost undeniable truth about how planetesimals form, something the New Horizons team didn't expect. Planetesimals form when smaller objects come together to make larger bodies, which may eventually combine to create a planet. Until now, there have been two competing theories: hierarchical accretion, which proposed that small objects would crash into each other at high speeds until they created something bigger, and local cloud collapse, where nearby objects would slowly come together because of their gravitational attraction, thereby forming larger and larger bodies. And now, thanks to the Arakoth flyby and important research into the object's geology, geophysics, composition and formation, we can be fairly certain that the theory of local cloud collapse is correct. The object's smooth surface and the lack of fractures from stress confirm that the cosmic snowman formed at low speed. Alan Stern, a planetary scientist and the lead for the New Horizons mission, said that the evidence was so strong, we've decisively solved a multi-decade debate about how planetesimals form. And thanks to New Horizons, we get to see the most famous Kuiper Belt object, Pluto. The spacecraft performed a flyby in 2015, allowing us to get up close and personal like never before and take those stunning images. The mission collected observations of Pluto and Charon, the dwarf planet's largest moon, and was able to collect data on Pluto's other satellites, Nix, Hydra, Kerberos, and Styx. Of course, we've all seen the stunning photographs of Pluto's heart-shaped surface region, also known as Tomba Regio. But did you know that the heart-shaped feature is actually a glacier? The western lobe of the heart, named Sputnik Planitia, after Earth's first artificial satellite, Sputnik 1, is a vast nitrogen glacier that stretches 1,000 kilometers wide and 4 kilometers deep, and is undoubtedly the largest known glacier in the solar system. The eastern lobe of the heart gets its light color from nitrogen that is carried from Sputnik Planitia and deposited as ice. Not only did we get stunning images of Pluto, but the data from New Horizons forever changed how we understand our favorite dwarf planet. It revealed that Pluto is far more complex than we previously thought, and offered clues to the origin of its heart-shaped feature. The data led some to believe that Pluto's heart-shaped region could be explained by an internal water-ice ocean. However, a recent study led by astrophysicist Harry Ballantyne from the University of Bern has revealed another, more likely culprit. The heart shape may have been caused by a low-velocity impact that left a gigantic splatter across the surface of Pluto, creating the western half of the heart shape. This impact would have come in at an oblique angle, as in not straight on. Imagine throwing a water balloon across dry pavement in the same way you might skip a stone across a pond. When the balloon scrapes the pavement, it pops, leaving an elongated splat of water across the pavement. This kind of angled, low-velocity impact is similar to how the western lobe of Pluto's heart feature may have been created. But it's not just Pluto that we get to see up close. The images of Pluto's moon Charon were also incredible. Can you make out the enormous equatorial tectonic belt? Its existence suggests a long-gone water-ice ocean on Charon. So what comes next in our quest to understand the Kuiper Belt and, consequently, to understand our solar system? New Horizons is expected to exit the Kuiper Belt sometime between 2028 and 2029. And while there is no current target for a further flyby, it is possible that NASA identifies another suitable target. New tools like the James Webb Space Telescope could help us to further analyze the composition of Kuiper Belt objects. And perhaps in the distant future, a robotic mission might allow us to land on one of these mysterious objects, or even collect a sample for a return mission back to Earth. Who knows what else we'll discover out there in this vast frozen frontier? As technology advances, Future missions will hopefully push deeper into the Kuiper Belt, revealing more of its long-held secrets, one icy world at a time.
The Solar and Heliospheric Observatory, also known as SOHO, recently celebrated its 25th anniversary in space. During these 25 years, it has observed the solar wind, watched out for dangerous coronal mass ejections, and observed the atmosphere of the Sun. An unintended consequence of its observations around this region were the discovery of over 4,000 sun-grazing comets, most of which we had no idea existed until they came into SOHO's view. And SOHO isn't the only solar observatory. The Stereo spacecraft and the Solar Dynamics Observatory have all seen new comets. And what's so cool about that is that they weren't designed with that in mind at all. I'm McColgan and you're watching Astrum, and in this video I wanted to look at some of the most impressive of these comets, try to understand how they interact with the Sun and how the Sun interacts with them. Sun grazers are comets that do just that. They graze the Sun as they pass, with the closest parts of their orbits taking them within a hair's breadth of the Sun's surface. Often they will pass through the Sun's huge atmosphere, called its corona. These comets are mainly long-period comets, comets whose orbits take hundreds to thousands of years to complete. Because of their orbit's extreme elliptical nature, they build up tremendous speeds as they approach the Sun, sometimes accelerating to 0.2% of the speed of light, an absolutely incredible speed for a particle, let alone a house-sized object. The majority of sun-grazer comets actually all originate from one large comet that was ripped apart several hundred years ago. This group of sun-grazers, shown in red in this video, is known as the Kreutz sun-grazers. What tends to happen over time is that the fragments from the larger comets spread out, meaning that there is probably a steady flow of them. As the largest of these comets also pass by the Sun, they too break apart into even smaller comets. And the reason we believe most sun grazers originate from the same comet? Well, they all tend to follow the same orbital path. The brightest comet in the last millennium, known as Comet Ikea-Secchi, was probably a fragment. It was so bright as it approached the Sun that it could even be seen during the day. You may have heard of another famous fragment of this comet that dimly illuminated the sky in the southern hemisphere in 2011, called Comet Lovejoy. While Comet Lovejoy wasn't as bright to the naked eye, it did make for some very impressive long exposure images and was seen by all the Sun observing satellites. Comet Lovejoy was not expected to survive this encounter, as it would have been in the Sun's 1 million degrees Celsius corona for more than 1 hour. However, astonishingly, it fizzed away from the other side of the disk, mainly intact, although probably severely impacted from the experience. The same thing happened to another comet, Comet Ison. You may remember that Comet Ison was expected to be a bright comet, potentially visible to the naked eye when it passed by the Sun in 2013. Alas, that wasn't to be. However, it still made for good viewing for the Sun observing satellites. Ison's approach was bright and impressive, and upon reaching the other side of the Sun, it faded out. Scientists can't be sure if the nucleus survived or not, but if it did, there are certainly no volatile substances on it anymore. All that's left is probably dust. However, these are some of the biggest Kreutz sun grazers we've ever observed. Their nucleuses maybe being a few hundred meters in diameter. Some of the smaller comets were not known about until they actually came into the view of a Sun-observing satellite. Due to their small size, being only tens of meters across, many of the smaller comets were completely snuffed out by the Sun immediately after passing by too closely. Which means unfortunately, they were vaporized pretty much immediately after they got discovered. Sometimes they will pass around the back of the disk of the Sun, never to re-emerge from the other side. Although at other times, the angle of the comet's orbit means we can witness this vaporization as it happens. At this distance from the Sun, the heat is incredible and the gravity is overwhelming. The icy comets not only evaporate quickly, but the rocky elements of them are also ripped apart from tidal forces. Our own close encounters with comets show that they tend to be structurally weak and very porous, sometimes nothing more than a pile of rubble held together by its own gravity. So combine that with the influence of the sun, and even the largest sun-grazer comets will come away heavily scarred. Now, there's an interesting phenomenon that happens when a sun-grazer passes by the sun, and that is that a CME will go off at the exact moment the comet passes by. There are numerous examples of this. However, scientists are still of the opinion that there is no mechanism for a sun-grazer to cause a CME. These comets simply aren't big enough to have any consequential impact on the sun, so it is currently believed that these examples you see here are purely coincidental. What scientists enjoy about sun-grazers though, is that while we can't send probes deep into the sun's corona, it's simply too hot for that, we do have these thousands of comets that are willing to take the plunge for us. And comets are perfect for us to observe what we are looking for, which is to better understand the magnetic fields within the corona, so that we can better predict CMEs and space weather generally. Look how as a comet passes by, its tail wiggles. The particles in the tail get heated so much they turn to plasma, which can easily be seen by the UV cameras of the satellites. Plasma reacts strongly to magnetic fields, so the wiggle you see in the tail is believed to be due to the way in which the tail interacts with the magnetic field lines in the corona. Currently, space weather is something we don't have a complete understanding of, so as more comets pass through, the more we will begin to understand that environment. So there we have it, some of the most impressive looking sun-grazers caught on camera by satellites that weren't even designed for them. Have you ever been fortunate enough to see a comet? What was your experience like? I'd be interested to hear your stories in the comments below. Thanks for watching.
This video was in part made possible by all the astronauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.